So hello, everybody. I'm going to be talking about deep reinforcement learning for detection of abnormal anatomies. I'm a PhD student at DTU Compute, and this project is carried on collaboration with Otico Medical. The detection of abnormal anatomies in medical images has a key role in accurate diagnosis making. The detection of the different types of malformation in the clinic is usually done by clinicians by observing different medical images, which links this decision directly to their experience and their expertise. There have been different deep learning models that have been trained to detect anomalies, and some of them are very successful. However, this requires for a large amount of data. And what it's even more complicated is that this data needs to faithfully represent all the spectrum of malformations, and this is a lot of times very complicated due to the uniqueness of some of those malformations. What we propose is using a deep reinforcement learning model, which is based on landmark location of certain anatomical points in CT images. And we propose to train that model in normative data and be able to detect the anomaly based on the variability of the output when facing an abnormal anatomy. The motivation behind this project is what's called cochlear implants. I'll explain a little bit the concept for some of you that might not be familiar, but when a person hears a normal hearing person, the process is that the audio stimulates the eardrum and makes it vibrate. So this vibration is transmitted to the ossicles and later to the cochlea, which is this snail-shaped like structure, which maps the different frequencies of the vibrations to electrical impulses that are sent through the nerve to the brain, and this gives us the sense of hearing. Cochlear implants consist of an electrode array that is placed on the cochlea, and there's an external microphone that captures the audio signal and a sound processor that that encodes it and sends it to the electrode array. So the different arrays activate according to the different frequencies, and a person that could not hear is able to perceive sounds. You may be familiar with some of the videos of kids or people that are being implanted and hearing for the first time. I couldn't resist to put a small clip here, so I don't know if you can hear it. I hope yes.
No, it's not coming through. Sorry, but
oh, okay. Well, however, I have it on my medical images of the inner ear are used to diagnose and evaluate the feasibility of implanting a patient with a cochlear implant, as well as to plan the surgery. So we wanted to look at those images and try to be able to detect the inner ear malformations, which are approximately 20% of the congenital hearing loss cases, so people that are born deaf or almost deaf. There are different categories of malformations. However, it's not a discrete spectrum, so it's not very categorical, but it's more of a continuous space of malformations because it depends on which point of the development something went wrong. Another important thing to consider is that we're going to be using clinical images, which are these ones on the bottom, compared to the type of images that are usually used in research, which are micro CT scans, which they present higher resolution. You can see the cochlea here, which will be the same as These are usually obtained from cadaveric data and are used for research, but we want to test this algorithm in the real images that are used in clinical practice. So we designed a set of landmarks that are not placed in the cochlea, but in some nerves that are in the nearby region. We have the facial nerve, which is that one, and the cochlear nerve. And we distributed them in different points that are quite unique. So the landmarks have some unique features. And here's an example of the annotations in a CT scan. So the approach is that we're gonna use those landmarks annotated in normative data, so in patients that have normal anatomy, to train a deep reinforcement learning model that will be able to estimate the location of those landmarks in an unseen new image. And we also expect to use those landmarks and the distribution of those landmarks to do a shape analysis. So we expect to be able to align all of this using Procrustes and project them in a PCA space of lower dimensionality. So we can imagine that a new CT image comes through, and then we'll use deep reinforcement learning and locate those landmarks. And that landmark configuration will be aligned accordingly to the normal data and projected to the PCA space. And we'll use the variability in that space to detect whether the anatomy is normal or abnormal. So we're going to use deep reinforcement learning for landmark location. I assume most of you are familiar, but reinforcement learning, it's a field of machine learning in which an agent learns an optimal policy for a certain task by interacting with an environment. So the agent observes a state, takes an action according to that state, and receives a reward based on that action. And by doing this iteratively, it's how they learn. In our current scenario, the environment is the 3D image scan, and the state is a cropped region that is centering the agent's location. The set of actions is the possible movements, so the 6 directions: up, down, right and left, and forward and backward. And the reward signal, it's a function of the difference between the current distance to the target landmark and the previous one. So it will be positive if the agent is moving closer to the target landmark, and negative otherwise. What's called the Q value, it's the expected reward of a certain state and a certain action. So of taking a certain action in a certain state. The DQ network of this type of problems, it looks very similar to an image classification network, in which we have some convolutional neural network layers, in this case of 3D, since it's volumetric data. And then we have some fully connected layers that map the final feature map to the output, which will be the Q value of each of the possible actions for the agent in that state. So in this case, it will be of size 6. More specifically, we're going to use the communicative multi-agent reinforcement learning model, which benefits from using multiple agents and the interaction between them. These agents communicate in 2 ways. They communicate implicitly because they all share the same convolutional neural network layers. Each of them has their own set of fully connected layers, but they also share some average of these weights, and that helps them to share some information. And this communication has been shown to increase the performance of these agents in this type of problems. We're using a multi-scale approach also, which means that the state or the crop region centering the agent initially is bigger, and it gets smaller as the agent is getting closer to the landmark. So this has a big resemblance on how humans or doctors in this case will interact with the 3D image, because first you will try to allocate the ear, the inner ear part within the whole, like the full head CT scan, and then you can try to find the cochlea or the different nerves. We define that an agent is ready to move to a smaller scale or that has reached the final location through oscillation. And yeah, we have a data set of 120 CT scans that are from cochlear implant patients, but that all of them have normal anatomy. We are going to use 97 for training and validation and 23 for testing. Then we're going to train 21 agents. So we had 7 landmarks. So that means we're going to be using 3 agents per landmark to increase the accuracy of the output. Here is an example of how the agents try to find different landmarks. This is an example with 7 agents, and you can see how the ROI or the state size gets smaller as they are getting closer to the final location. So the analysis that we expect to do with these landmarks is that we use the annotated landmarks for the normative data to build a point distribution model. So we use Procrustes analysis to align all these different shapes, and from that we extract what we call the mean shape. And then by projecting all these aligned shapes into PCA, we can extract the principal components and also the weights that will weight the different principal components that explain the variability in this new space. So in that sense, we can, by computing the residuals of a new shape with the main shape and project those to the principal components, we can obtain the coordinates in the new PCA space defined by the normative data. So more visually, we know that for each landmark, we have 3 agents. So, and we're gonna use the 5 first landmarks. So we have a set of 15 agents that will we assign randomly to 3 shapes, and those shapes are aligned with the main shape using Procrustes, and then they are projected in the PCA space. So what we're gonna do is that we measure the distance between those projections, and we'll use as an evaluation metric the standard deviation of those measurements between the projections. To test our hypothesis, which is that the agents will not converge. Given an abnormal anatomy, the agents will have a harder time to converge to the same location. This is not a stochastic process because the agents have different initialization locations within the image. They are all initialized within the 80% of the image, but it's random each time. So we assume they will have a low degree of agreement, which will be shown with a high standard deviation of those distances. So what we did is that we generated an abnormal CT scans artificially. We did this by erasing the cochlea structure. We substituted it with Gaussian noise with the same mean and standard deviation of the surrounding tissue. And we use this data set to test our hypothesis. We choose also 6 dimensions of the PCA because those were already explaining 90% of the variation of the point distribution model, and 5 landmarks, as I said previously, and we're gonna do it for 5 runs to get a statistical significance. And here are the results. So on the left, you can see the results using the point distribution model and the PCA projection. So this is the standard deviation for the different images of the test set. You can see that it is significantly higher for abnormal images, so for the artificially generated abnormal images rather than for the normal anatomy. And we also see a very positive ROC curves, which they, even for all the runs, we see a good degree of accuracy. And what is more important, when using all of the runs, we have a maximum accuracy of 96%. And we tested this against just using the distance in the image space. So we will compute the mean value of the standard deviation of the agent's distance for the same landmark, just to see if actually doing the point distribution model and the PCA projection was also was actually giving us an advantage against just the normal space. And we could see that even though there's still a significant higher standard deviation for the abnormal cases, the method is not as robust and the accuracy is slightly worse, which means that of course our hypothesis that the agents will have a harder time converting to the landmark was stands. And this has been everything from me now.